Welcome to G Fun Facts Online. For centuries, Mars has been our celestial neighbor, a world of red deserts and white ice caps that has fired our imagination. We've sent rovers to scour its surface and orbiters to map its terrain, building an incredible picture of its surface geology and its thin, cold atmosphere. But its deepest secrets, thousands of kilometers beneath the rusty soil, remained locked away. Until now. In a discovery that is completely rewriting the history of the Red Planet, scientists have finally listened to the very heart of Mars, and they've found that it has a solid inner core, just like Earth. This isn't just a minor tweak to our planetary models. This single fact is reshaping our entire understanding of how Mars formed, why it lost its chance at being a habitable world, and how it became the cold, desolate planet we see today. Before we had the tools to listen directly, our knowledge of the Martian interior was basically educated guesswork, a collection of clever inferences from indirect data. Orbiters flying around Mars could meticulously map its gravitational field. Tiny variations in gravity would reveal denser or less dense regions below the surface. We could also measure the planet's moment of inertia by observing how it wobbles on its axis. This told us how much of its mass was concentrated towards the center. Together, these clues strongly suggested that Mars was a differentiated world, meaning it had separated into layers, a crust, a mantle, and a dense metallic core. But the precise nature of that core remained a huge question mark. Was it a giant, sloshing ball of molten metal? Was it entirely solid? Or was it layered like Earth's? Scientists had competing models, each with good arguments. Some theories proposed a very large, entirely liquid core, one that was rich in lighter elements like sulfur, to explain the lower-than-expected density. Others suggested a solid inner core might exist, but without any direct evidence, these were just sophisticated conjectures, impossible to prove or disprove. The challenge was immense. How do you perform an ultrasound on an entire planet? How do you see into a heart of iron buried under thousands of kilometers of rock? The answer came in the form of a three-legged, one-armed robot named InSight. The name is a perfect acronym: Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. Its purpose was simple and profound: to take the vital signs of Mars. InSight landed in a flat, plain-like region called Elysium Planitia in November 2018. Its mission was unique. It wasn't there to look for life or drive around. It was there to sit perfectly still and listen. Its primary instrument was an incredibly sensitive seismometer called SEIS, the Seismic Experiment for Interior Structure. This dome-shaped device was so sensitive it could detect ground movements smaller than the width of a hydrogen atom. The lander's robotic arm had to carefully place SEIS directly onto the Martian surface and then cover it with a wind and thermal shield to protect it from the harsh environment. The goal was to detect Marsquakes, the faint tremors that ripple through the planet from shifting rock, as well as the seismic shaking from meteoroid impacts. For 4 years, until dust finally covered its solar panels in late 2022, InSight sat and diligently recorded the seismic whispers of Mars. That data has become a goldmine for planetary scientists, a new language with which to understand the planet. Now, the initial analysis of InSight's data, which came out in 2021, actually seemed to paint a slightly confusing picture. The first readings, based on quakes that were relatively close to the lander, pointed towards a large, entirely liquid core with a surprisingly low density. This was a bit of a problem. The composition just didn't quite line up with what we thought the elemental building blocks of Mars were, based on meteorite samples and our models of solar system formation. It was a puzzle. It suggested the core had to contain an enormous amount of lighter elements like sulfur to bring down the average density. But, as we've learned time and time again in science, sometimes the most interesting discoveries come from data that doesn't quite make sense. The key to solving this puzzle, and to seeing even deeper into the planet, lay in detecting seismic waves from quakes that happened on the complete opposite side of Mars. These far-side events are much harder to detect because the waves lose a lot of energy traveling through the entire planet, but they are invaluable because they are the only waves that travel directly through the planet's absolute center, giving us the most detailed view possible. This is where the real breakthrough happened, thanks to a meticulous reanalysis of the data by a team of scientists. To understand what they found, we need a quick primer on seismic waves. When a quake happens, it sends out different types of energy waves. The two main types are P waves or primary waves, and S waves or secondary waves. P waves are compressional waves, like sound, that can travel through solids and liquids. S waves are shear waves that move material from side to side, and they can only travel through solids. The fact that S waves from quakes don't pass through Earth's outer core is how we first figured out it was liquid. The scientists looking at the Mars data were focused on a special type of P wave, known as a PKP wave. The P indicates it's a P wave, and the K is the code geologists use for a wave that has passed through a planet's outer core. So a PKP wave travels down from a quake, through the mantle, into the liquid outer core, and back out through the mantle to the seismometer. The team focused on two very special variations of these waves. The first type is called PKKP. Imagine a quake happening on one side of Mars. A PKKP wave travels down through the mantle, crosses into the liquid outer core, travels all the way across, and then bounces off the underside of the core mantle boundary on the far side of the planet. It then travels back through the outer core and the mantle to be picked up by InSight. This tells you a lot about the size and properties of the outer core. But the second type of wave, the one that changed everything, is called PKIKP. That little I is the key. It stands for inner core. These waves also journey down through the mantle and into the liquid outer core. But instead of bouncing off the far side, they travel deeper and reflect off the boundary of a solid inner core before making their return journey. Detecting this reflection is incredibly difficult. It's like trying to hear the echo of a whisper from across a continent. But by carefully analyzing the data from two specific far-side events, the research team found it: the faint but unmistakable signature of PKIKP waves. Here's the smoking gun. These PKIKP waves were arriving at the seismometer earlier than they should have if the core were entirely liquid. Seismic waves are like runners in a race. They move at different speeds depending on the material they're running through. And crucially, they speed up when they pass through a solid compared to a liquid. The fact that these waves got back to InSight ahead of schedule was the definitive proof that they had taken a shortcut through a solid object deep in the center of Mars. The silent planet was finally telling us about its heart. And what a heart it is. The data revealed a solid inner core with a radius of about 600 to 613 kilometers. That's a solid ball of metal about 375 miles across. This solid heart is then surrounded by a liquid outer core, bringing the total radius of the entire Martian core to roughly 1/800 kilometers. Now here is a truly mind-bending fact that highlights the importance of this. This solid inner core of Mars makes up about 18% of the planet's total radius. Why is that so incredible? Because Earth's solid inner core makes up about 19% of our planet's radius. The similarity is uncanny. This suggests that the deep, fundamental processes that govern how planets form their cores, how material differentiates, cools, and crystallizes, might follow a more universal recipe than we thought. It suggests that, despite their different sizes and final fates, Earth and Mars started their lives on a remarkably similar path. The seismic waves didn't just tell us that the core was there. They also gave us crucial insights into its composition. Like Earth's, the Martian core is primarily an iron-nickel alloy. but the data shows it's less dense than a pure iron-nickel mixture. This points to the presence of a significant amount of lighter elements mixed in. Scientists now estimate that a staggering 20% of the Martian core's total weight is made up of these light elements. The main ingredient seems to be sulfur, but there are also smaller amounts of oxygen, carbon, and even hints of hydrogen. This cocktail of elements is like a chemical fingerprint, a message in a bottle from 4.5 billion years ago, telling us about the specific conditions in the protoplanetary disk when Mars was first forming. The presence of all these lighter elements also lowers the melting point of the core material, which has profound implications for the planet's long-term thermal history. And importantly, this new, more complex model, a smaller, denser liquid outer core surrounding a solid inner core, also perfectly resolves that earlier puzzle of the seemingly low-density liquid core. The first calculation in 2021 was averaging the density of both the liquid and solid parts together. Now, with the two layers separated, the densities of each part make much more sense in the context of planetary formation models. The picture is clearer, more consistent, and much more elegant. This brings us to what is perhaps the most significant consequence of this discovery. It has to do with Mars' ancient past and its tragic transformation from a potentially warmer, wetter world into the frozen desert we see today. The entire story hinges on the planet's magnetic field, or more accurately, its lack of one. Here on Earth, we are protected by a powerful global magnetic field. It's generated by a process called a geodynamo. Think of our planet's core as a giant electrical generator. We have a solid inner core and a liquid iron outer core swirling around it. As the Earth cools over billions of years, the solid inner core slowly grows as iron crystallizes onto it. This process releases both heat and lighter elements into the liquid outer core. This makes the liquid buoyant and causes it to churn and convect vigorously, like a pot of boiling water. This motion of a conductive fluid creates powerful electrical currents, and those currents generate the magnetic shield that envelops our planet. This shield is absolutely essential for life. It deflects the constant stream of charged particles from the sun, known as the solar wind, and protects us from dangerous cosmic radiation. Without it, the solar wind would strip away our atmosphere and boil off our oceans. Now, we have very strong evidence that Mars once had a powerful magnetic field too. In the ancient southern highlands of Mars, there are vast regions of crustal rock that are still strongly magnetized. They hold a fossilized record of a global magnetic field that was active billions of years ago. A Martian magnetic shield would have been crucial for protecting a thicker, denser atmosphere. And a thicker atmosphere would have created enough pressure to allow liquid water to be stable on the surface, carving the incredible river valleys, deltas, and lake beds that our rovers like Perseverance and Curiosity are exploring today. But for reasons that have long been a central mystery in planetary science, that magnetic field vanished about 4 billion years ago. The leading theory for decades was that Mars, being a smaller planet than Earth, simply cooled down faster. The idea was that its entire core just solidified, grinding the planetary dynamo to a halt. The engine just seized up. This new discovery of a still liquid outer core and a solid inner core completely upends that long-held scenario. In fact, it's quite the opposite. The very structure that we have now discovered, a solidifying inner core surrounded by a convecting liquid outer core, is precisely the kind of structure you need to generate a magnetic field in the first place. The discovery proves that Mars had the right kind of engine. So the question changes. It's no longer did Mars have the right core structure for a dynamo? The answer is a resounding yes. The new question is, why did the dynamo die? The answer likely lies in the specific chemistry of the core and the rate at which it cooled. While the crystallization of the inner core does release heat and stir the liquid outer core, the process on Mars may have become too sluggish over time. Perhaps the large amount of light elements, like sulfur, changed the thermal properties of the core in a way that made convection less efficient. The engine didn't seize, it just couldn't maintain the horsepower. The convection in the liquid outer core weakened until it could no longer sustain a global dynamo. And once that protective magnetic shield failed, the solar wind was free to relentlessly blast the planet. Over billions of years, it stripped away the Martian atmosphere, atom by atom, causing the atmospheric pressure to drop until any liquid water on the surface either evaporated into space or froze into the subsurface ice we find today. The discovery of the solid core doesn't change the outcome for Mars, but it gives us a much more accurate and nuanced story of how it happened. It's a story of a planetary shield that failed, leading to a world that lost its potential for life. Unmasking Mars' solid core is a monumental achievement. It's a testament to the power of seismology, a science that allows us to explore the unseen. This discovery was decades in the making, building on the legacy of the Apollo missions, which first placed seismometers on the Moon. The success of InSight, a fantastic collaboration between NASA and its European partners, has now written the playbook for how we can explore the interiors of other planets and moons in our solar system. This new, deeper understanding of Mars has far-reaching implications. It provides critical new data for our models of how all rocky planets form and evolve, not just in our solar system but around distant stars as well. By directly comparing the cores of Earth and Mars, we can finally begin to understand in detail why two worlds that may have started with similar ingredients took such wildly different evolutionary paths, one becoming a vibrant haven for life, the other a cold, rusty ghost of a world. Of course, while this discovery answers a huge question, it also opens up exciting new lines of inquiry. There is still so much to learn. What is the exact composition and proportion of those light elements in the core? What is the precise temperature at the very heart of the planet? Can we reconstruct a more detailed history of the rise and fall of the Martian dynamo? Future missions to Mars will almost certainly carry new generations of more advanced seismometers. The dream is to one day have a whole network of them spread across the planet. With multiple listening posts, we could use a technique similar to a medical CT scan to create a detailed, three-dimensional map of the entire interior, from the crust to the core. Such a network could even search for evidence of mantle plumes, hot upwellings of rock from the deep interior that might be driving some of the observed seismic activity. The story of Mars is a story of planetary change on the grandest possible scale. The discovery of its solid inner core is a pivotal new chapter. It's a powerful reminder that the greatest secrets of the cosmos are often buried deep beneath the surface, just waiting for the right tools and the right minds to bring them into the light. For 4 years, the InSight lander sat and listened patiently. The silent planet has now spoken, and in its seismic whispers, we are finally hearing the epic story of its birth, its life, and its slow, silent decline. We're piecing together the history of a world that might have once been much more like our own.